In the last video, I talked about Millikan's detailed measurement of photoelectric effect and how it verifies Einstein's predictions and theory very clearly. Now, the last set of his measurement that I want to talk about is how he was able to use his measurement to obtain a value of the Planck's constant, the value of h. Now, to see how this was done, recall that in Einstein's equation, that the maximum kinetic energy is equal to the photon energy minus the work function, right? And that the maximum kinetic energy is related to the stopping potential, because it is used to do work against the stopping potential. So therefore it is equal to charge of the electron times the stopping potential. So we have such an equation. And the idea in Millikan's measurement to measure Planck's constant, meaning to measure the h here, that's the Planck's constant that Millikan measured, is simply to plot a graph of the stopping potential against F. Because if you look at Vs and look at F, they are like what you see in a straight line graph. Yeah, you know, if you look at a straight line graph, let me rearrange this into this form. Vs is equal to, divide both sides by E, I get h over E times F minus pi over E. Okay, so the equation, Einstein's equation, looks like this. Now compare this with a straight line equation. Y equals to mx plus c or b, depending on where you are. If you compare the two, you see that if we think of Vs as y and F as x, then h over E would just be the gradient, and phi over E would be the c, which is the y-intercept. So this means that if I plot a graph of stopping potential against frequency of the light, I can just and I can find the gradient and calculate h, since we already know what E is from Millikan's own experiment, maybe some years before this. So that makes it possible, therefore, to use this idea to actually find and measure the Planck's constant. So let me just sketch out this graph to get a better idea, clearer idea on the steps. So right, I want to use the data from this measurement to plot my graph. Now, how can I do that? Right, I need a set of values of F and the corresponding stopping potential. So let's say for this value of F, when I use green light, the stopping potential would be, say, this value. Let me call it V1. So that has a minus sign. Let's say when I use blue light, the stopping potential right? Let's say for the green light, the frequency is f1. For blue light, let's say frequency is f2, and the stopping potential is minus v2. For the purple light, violet light, let's say it's minus v3 is the stopping potential, and the frequency is f3. So suppose that we have all these numbers, right, which Millikan did when he did this measurement. Then we can plot the graph. When green light was used, the frequency was, say, f1, and the voltage was v1. So let's say we have a point somewhere there, the voltage v1. Okay, so that gives us a point. When blue light was used, let's say the frequency is f2 is here, and the voltage is v2. So this gives us another point. And when violet light was used, the frequency was f3 somewhere there, and the stopping potential was v3 that Millikan measured. So that gives us a third point. And Millikan might have, measured a few other points. So we have he found a straight line, and we can now draw a line through this graph. Okay, so this graph, this is a straight line graph, and we can find the gradients from this graph. Actually find the gradient, and if we find the gradient, okay, we would actually be able to calculate the Planck's constant. Now I don't actually have a Millikan's graph. I think you can find it on the internet. You can find the paper that he wrote. I think it goes something like on the measurement of Planck's constant using photoelectric effect, something along those lines for the title. You can actually find it if you search those words and Robert Millikan. But let me just do a simple exercise using this graph, not using Millikan's actual data, but using what values we know about, say, the frequency of maybe green light and the work function. So you see, first of all, the frequency of green light right, let me just take for example that this is plotted in units of 10 to the power 14 Hertz. Okay, so that would be hundreds of terahertz if you remember from an earlier video. And let's say the value in this unit for the green frequency for this particular green frequency is 5.706. So times 10 to the 14 Hertz. Okay, now I don't actually have a value for the voltage, but there's something that I do have. Imagine extrapolating, that means extending this graph all the way down here until we get a y-intercept. What is this y-intercept? That is the y-intercept. If you look at this value here, minus phi over e is the y-intercept. So phi is the work function. If you divide work function is energy, and that's in joules. If you divide energy by E, you get the energy in units of EV. Okay, and we do know the EV. We do know the work function of sodium in EV. I've written it down in an earlier video. These are values that I got from Wikipedia when you look for work function. That is 2.28 minus 2.28. Okay, so that would be in volts. Okay, so we can actually let me make a correction. When I said the green light has this value, I'm referring to the threshold frequency. Right, the threshold frequency of sodium is actually in the region of the green light region. So this value is the value of the threshold frequency of for sodium. Now this is a value which I actually calculated by working backwards after knowing all these values. So it's a bit like cheating. I'm not actually doing this experiment, but let's just suppose that we have the graph and this has been measured, and let's say that these are the actual values we see on Millikan's graph, which is pretty much what it would be, right? When Millikan carried out this experiment properly, right? So if he had used sodium, when you extend this graph, you would actually be able to read off these numbers, and we would expect that these are pretty much the numbers, close to the numbers that you would actually see if you had used sodium metal. So therefore, assuming that this is the graph that is measured, and these are the values that you see on the x-intercept and the y-intercept, we can now find the gradient. Okay, so we would say that the gradient is h over e. Gradient, which is h over e, would be equal to, and I can just make use of this triangle directly. So vertical over horizontal. Okay, so that would be 2.28 divided by this 5.706 times 10 to the power of 14. And since we know what E is, as we know, E is actually 1.6 times 10 to the power of minus 19 coulombs. Therefore, we can just bring E over and calculate H with our calculator. If you do that, you'll find 6.63 times 10 to the power of minus 34 joule second. Now I've been using the name Planck's constant for this H, and I realized that I sort of slipped it in this and in the last video. So let me just write out the name of this H. Planck's constant. That's the name of this number. Now there's some history behind it. It's a constant that was first discovered by another person called Max Planck at the start of the 20th century, in the 1900s, when he made a theory on black body radiation. So we shan't go into that except to say that Einstein made use of this constant from Planck's theory. That's why this is called Planck's constant. And at that time, Planck already has an estimate of the value for Planck's constant, and that was obtained from measuring the spectrum emitted when objects get very hot and start glowing. It's a completely different topic. But in this case, we have this room temperature glass tube, just some green, yellow, purple light falling on a piece of sodium and measuring the electricity. So completely a new experiment, and using Einstein's theory, it turns out that we can actually measure the same Planck's constant, right, and get more or less the same value. And with I suppose more accurate control and measurement of the frequency using diffraction grating, likelihood is that a very accurate measurement can be carried out and a good value of this constant obtained.